Hi, 5th grade. Welcome to your Earth's Motions and Seasons lecture. Go ahead and get your slides pulled up and we'll get started. It's chapter 12, pages 140 through 143. Let's jump right in and move on to slide 2, titled Isaac Newton. So we all remember him. He discovered gravity, apple fell on his head, blah, blah, blah. And he came up with the law of universal gravitation. It states that every object in the universe attracts every other object depending on their masses and distances from one another. So basically, this is saying everything has some amount of gravity in it, and they pull on each other. The greater something's mass is, the greater its gravitational pull. So the sun, which has a very large mass, pulls on the Earth. And the Earth has a mass which pulls on the moon. So we can state that as the mass of an object increases, the greater pull it has on something else. So between two objects, as the distance increases, the gravitational pull decreases. They can't pull on each other as much, and the inverse is true as well. So as distance decreases, as they get closer together, the gravity increases, pull more on each other. Remember that gravity is what affects weight. Weight is based on gravity. It's the pull of gravity on mass, which means that the object's weight depends on its position in the universe. But when we discuss this, we're discussing the object's mass, how much matter it's made up of. And remember, mass does not change no matter where you are. Whatever your matter is your matter. Okay? Whatever makes you up, makes you up. Whether you're a person or a star. So on slide 3, why does the sun pull on Earth? Well, we just discussed how the sun has a huge mass. It's pulling on the Earth. In fact, the sun's mass is around 330,000 times more than Earth, and it's closer to Earth than any other star. So if we had this thing that its mass is 100,000 times bigger than ours, it's going to pull us constantly. And this pull keeps the Earth rotating and in its little orbit, how it moves around the sun. And our pull on the moon is what keeps the moon rotating. Another key player into how the Earth stays in motion is inertia. We talked about inertia when we first learned about Newton's laws. Newton's first law states that an object at rest will stay at rest until acted upon, and an object in motion will stay in motion unless acted upon by an outside force. So basically, this law is saying, hey, the Earth's rotating until something makes it stop. It's gonna always rotate, okay? So let's move on to slide 4 and the seasons. Earth's rotation and its tilt on its axis is the reason that we experience the 4 seasons. So remember from your last lessons about the Earth, here's the Earth, and you can imagine that it has kind of a pole running through it on an axis, and it's slightly tilted. Imagine a globe that you spin in history class. It's the same exact thing. It's on a slight axis, and that's the reason we have our seasons, because it affects how the sunlight hits the Earth's surface. So if the sun's over here, and the northern hemisphere up here is tilting towards towards the sun, more sunlight will hit the northern hemisphere than the southern hemisphere. So it would be summer in the north, like say in the US, but it's winter down south somewhere like Argentina. And the equator does not experience extreme differences in season because it's in the middle of the Earth. It doesn't experience the tilt. It's the poles down to the equator that experience all the tilt. Rather, the equator has wet and dry seasons, so it gets more rain in the summer and less rain in the winter. In summer, because there is no tilt in the equator has close to or all 24 hours full of sunlight. The sun doesn't go down. It may be lower in the sky, but it never completely disappears in the summer in areas that are on the equator. The opposite of that is that in the poles, in the north and south poles during winter, because the sun's over here and during winter, they're tilted away. So let's pretend the North Pole's up here. It's tilted completely away from the sun. It's not getting sunlight. So during the poles, it is continuously dark for 24 hours a day. Alright, so on to slide 5, solstice. You've probably heard about the winter solstice and the summer solstice before. So a solstice is when the sun's most direct rays reach the farthest north and south. Really, it's the brightest or longest days of the year for summer, or in winter, the shortest day of the year, the darkest. It's the extremes. It occurs twice a year. In the summer, it's on June 22nd. That's our longest summer day. So go out on June 22nd and take in all the sunshine you can. And in winter, on December 22nd, is when the winter solstice is. So it's going to be really, really short daylight. Sun is probably going to set really early in the evening, and you're going to be sitting there thinking, I should be going to bed. But it's only 4 p.m. So this occurs because when the Earth is on its tilt, at these points the Earth is on its maximum, the amount that it can tilt towards or away from the sun. Lastly, we have our equinox slide 7. So this is when the day and the night are almost the same length everywhere around the Earth. So the Earth is tilted at the least amount. And it's because of this tilt that neither of the poles are really closer to the sun than the other, because remember, when you tilt, here's our sun, and let's say we're tilted this way, the northern hemisphere is closer to the sun and the southern is farther. Or the opposite is true when it's winter in the northern hemisphere, like here in the US. But at this point, the sun appears to pretty much be directly over the equator, and so day and night are almost the same exact length. And in the north, the spring equinox is March 21st, and the fall equinox is September 22nd. Alright, that is your lecture for the day. Go ahead, and all you have to do for today is read pages 140 to 143. It goes over everything I just talked about. Have a good day!